Vegetable oils or butters are naturally occurring components of plants. They are obtained from seeds and fruits by pressing or extraction. In pharmaceuticals, they are used as excipients or carriers in pharmaceutical forms or as independent active ingredients. They are found, for example, in oil capsules to dissolve vitamins and are part of the lipid phase of emulsion systems, while an example of the active ingredient is castor oil, which acts as a laxative. Vegetable oils and butters have emollient properties, and those directly improve skin hydration, which is why they are also widely used in the cosmetics industry. Vegetable oils consist of triglycerides and unsaponifiable components. According to their chemical composition, triglycerides are esters of glycerol and fatty acids, which in most cases account for 98 to 99% of all compounds in vegetable oil. The fatty acids are saturated or unsaturated. Unsaponifiables, that is, phytosterols, squalene, phenols, terpenoids, carotenoids and vitamin E are present in about 2% of oils. The term unsaponifiable substances is a very broad term and includes many very different substances. All unsaponifiable substances have two things in common. They are not hydrolyzed in a reaction with a base and they are not water-soluble. Triglycerides are the carriers of physicochemical properties of oils and butters. Since fatty acids make up the majority of triglycerides in vegetable oils, those acids determine whether the oils are liquid or solid at room temperature. The higher the proportion of saturated fatty acids, the higher the melting point. The same applies to the stability of the oil. The more saturated fatty acids present, the more stable the oil. Vegetable oil is obtained by first separating it from the part of the plant in which it occurs. This is usually the seeds or the fruits of the plant. It is then ground or crushed. Vegetable oil is obtained by mechanical extraction, pressing, or by chemical extraction using solvents. A more modern technique is also on the rise: extraction with supercritical CO2. The extracted oil can then be purified and, if the intended use so requires, also refined or chemically treated. Refining means the removal of impurities or the purification of a substance. Refining removes components that affect the stability of the oil and components that affect the organoleptic properties from vegetable oils, preventing oxidation and the formation of harmful radicals. Refined oil is more stable when exposed to light, air and temperature. From a technological point of view, it is more suitable for using cosmetics and pharmaceuticals. Oil is refined when it is known that it will be exposed to high temperatures, when it is desired to extend the life of the oil or to remove or soften its color, odor and taste. The quality and properties of vegetable oils are evaluated by determining chemical numbers. These are saponification number or saponification number, peroxide number, iodine number, acid number, hydroxyl number and ester number. In this lab exercise, we will learn about the peroxide number. The peroxide number, IP, is a number determined via an exercise that tells us in milliequivalents of active oxygen the amount of peroxide in 1000 grams of the preparation or oil. It is an indicator of oxidative damage or brightness. The active site in oxidation is double bonds reacting with oxygen. The flammability of fats is shown in the early stage of oxidation by the formation of peroxides and hydroperoxides. There are two methods described in the pharmacopoeia to perform the test. We will perform our work according to method B. First, check the maximum allowable peroxide value in the oil's monograph. In the case of olive oil, the value is 20.0. Next, let us take a closer look at the implementation process. Depending on the expected peroxide value, weigh the prescribed mass into an Erlenmeyer flask. In our case, we weigh the mass exactly between 1.2 and 2.0 grams. We weigh the olive oil. Add isooctane and acetic acid in the right proportions and stir to dissolve the oil. If you are processing butter, you can heat the mixture slightly to melt the butter. Add 0.5 milliliters of previously prepared saturated Ki, measure for 60 seconds and mix intensely. The color will change to a more intensive yellow or brown. After 1 minute, add 30 ml of demineralized water. The pharmacopoeia states that starch should be added in the middle of the titration. However, to obtain reproducible results, we recommend adding 8 to 10 drops of starch just before starting the titration. The solution turns brown. Titrate with prepared 0.1 mol natrium thiosulfate. The color change is not very obvious and depends on the initial color of the oil. During titration, the brown color of the mixture changes back to yellow and the solution separates into two phases. In the image, we see a comparison between the previously titrated sample and the sample during titration. The initial and final color shade depends on the initial color of the oil and the brightness of the oil. For the calculation, we use the formula in the pharmacopoeia monograph for the peroxide number. For V1 in milliliters, the volume obtained during titration is used. For V0, a blank repeat must be performed, which should not exceed 0.1 milliliter. It is not necessary to convert milliliters. For C, take the molar concentration of sodium thiosulfate, which is approximately 0.1. The exact concentration must be calculated. The mass of the oil is expressed in grams. The result is then compared with the prescribed result from the pharmacopoeia to determine whether the olive oil meets the requirements.